What up, people? Hope you guys doing well. We want to get into this stuff today. And this is the sort of like the last lecture where we're going to be dealing with the constant source. So then the class takes off very, very fast. So what I want to do here is that I want to go in, share my screen, show you where we're headed, and then let's move on. So the first thing that we want to do here is that we want to go and review the problem solving strategies. And here's what we have. What we have here is that we have a four-step process. We need to determine the initial steady state. Now that we're with the inductor, we'll talk about IL of 0 minus. After the switch is thrown, I don't need the Thevenin, I need the Norton parameters. I short circuit, R Norton or Thevenin, and I need 1 over tau. Then I need to put it into the solution form, and then I got to go solve the circuit problem. Okay, that's the idea right there. So what we want to do is that we want to go in and we want to focus on that. So here we go. So I'm going to come back in here, go to the next lecture, and here we were. We were talking about circuit 7.3. And we should always try to intuitively understand what's going on, because like I said already, you don't want to rely on my mathematics purely. You'll get burned, I promise you. So we asked the question, does the inductor store or decay current? And I said my guess was that it decays current, because when I look at this current source over here, this is going to produce 500 milliamps. When this gets shorted out, I now have the 100-volt source. Well, the 100-volt source put out, more than 500 milliamps across the inductor? I don't think so. Because of that, I say it decays. So if my solution comes back and it's storing current, then I should be going like, okay, there's a problem. Okay, let's go do that. So I'm going to go through that four-step process. The first thing that I'm going to do is I'm going to determine the current initially. So that means I'm looking at 0 minus. So here I go. At 0 minus, what do I have here? Well, I have no source. I have a 600, 400, but at steady state, note that the inductor is a short. And then I have the current source. So here I go. So then my circuit looks like this. So I have a 600. And now my inductor is a short. And my guess for the current of the inductor is that it's going to be going in that direction. And then what I can see here is that this is connected to my 500 milliamp source. Clearly, the inductor, since it's a short, is going to kill off these guys. So these guys are killed off by the short of the inductor. So this tells me here is that IL of 0 minus must be 500 milliamps. So now I got my initial condition. So now the switch is thrown. When the switch is thrown here is that I now determine the Norton parameters. So there's 3 of them. There's I short circuit, Rn, and 1 over tau. So let's go look at those guys. So if I look at those guys, I have a new circuit. So I know that the 500 milliamp source is gone. So I got the 4, 4, 6, and the inductor. So now this is what my circuit looks like. I have my 100-volt source. I have 3 resistors. The 400, the 600, and 1 more 400. And then I have my inductor. So 400 and 600. And I know that this is my inductor right here, and I have this current IL of T. That's what we want to calculate. In the end, what we're going to calculate here is that we're going to calculate the voltage across the 600 ohm resistor. In other words, we're really after this guy right here. I'll call it Vx. I could have called it 600, but I'm going to call it Vx of T. That's what we want to look at. So let's go do what we're supposed to do here. So let's go. So the first thing I'm going to do is I'm going to determine I short circuit. So I'm going to determine I short circuit. So that means I'm going to remove the load and replace it with the short, right? Remove inductor and replace with short. So if I do that, then I'm going to have this circuit right here. I'm going to copy this just to be fast. And I have this circuit here. And so now I don't have an inductor here. So what I have here is that I have a short here. And this current is going in this direction. And that's I short circuit. Well, one of the things that I see here is that you could see that the current I short circuit is the current through the 400 ohm resistor. So what I'm seeing here is that I'm going to use VDR to get the voltage across the 400 ohm resistor. Now note, of course, I'm talking about the one on the right, not the one on the left. Okay, so I'm going to calculate that voltage and use Ohm's law to get I short circuit. Okay, let's do that. So the first thing that I see here is that the 400 and the 600 are in parallel. So if I use VDR, I could see here that it's really the voltage across the 400 is the same as the voltage across the 600 and 400 in parallel. So in other words, I'm going to get 400 in parallel to 600, 400 parallel to 600 plus 400 times my voltage source, which is 100 volts. So if I compute that, I'm going to find that the number that I get here is 37.5 volts. I now know what the voltage is. So now, using Ohm's law, I now see that the current of the 400 is then going to be the voltage of the 400 divided by 400. So when I compute that, I'm going to get a value that reads 93.8 milliamps. But remember, this is the same as I short circuit. So now I know what the current I short circuit is. So before we go, look at that current. That is going to be the final current of the inductor in the Norton circuit here. So if I compare 93.8 milliamps compared to what? 500 milliamps, we see that the inductor is definitely going to decay. So that was a good guess. Okay, so now let's go get RTH. So the next thing that we want to do here is that we want to determine RTH or R Norton. And what do? We short out the 100 volt source. So let's go do that. So if I short this guy out, what I'm seeing here is that I'm seeing what? I have no excuse me. I don't have the source anymore. So then that means here is that I have a 400, 600, 400, like this. So when I'm looking at R Thevenin or R Norton, it's in that direction right there. And so you could see here is that I have 400 in series with 400 parallel to 600. So if I do this here, you could see then that R Norton is then going to be 400 plus 400 parallel to 600. And if you compute that, you're going to get a value of 640 ohms. And that's going to be my Norton resistance. So now that I have that, I have to go calculate the inverse of tau. So now we want to determine 1 over tau, where tau for the inductor is going to be L divided by RTH. Okay, so here we go. So I'm going to get 1 over tau is then going to be RTH divided by L. So I actually don't know what the value of L is. It's 0.1. So if I come here, this is going to give me 640 divided by 0.1. We could see that this is 6,400 hertz for 1 over tau. So now we got all the Thevenin parameters, and now we're going to write out the solution here. So if I write out the solution here, what we're going to see here, so now I'm going to put into solution form. So then we know that the inductor must look like this here. So the inductor current has to be I short circuit plus IL of 0 minus I short circuit e to the minus t over tau. So if I start putting in my numbers, I know that I short circuit was 93.8 plus this should be 500 minus 93.8 e to the minus 1 over tau, which is 6,400 t, and of course this is in units of milliamps. So if I punch this into my calculator, I find that the solution that I have then is 93.8, and then I'm going to get 406.2, and I know that there's a lot of sig figs here, but it turns out that I ended up p-spicing this to make sure that everything did well. And then this is going to be e to the minus 6,400 t milliamps. What's the important thing? This is a plus sign. Okay, so here is the current of my inductor. So I now have my solution. Once again, what does that plus sign mean, right? This tells me I have a decaying current. And just to make sure, right, just to make sure, what am I seeing here? What I'm seeing here is that I have my, if I plot this thing, this is what I'm seeing. I'm coming in at 500 milliamps. And then what's it going to do? It's going to decay. What's it going to decay to? It's going to decay to about 1/5 of its value. And so I know that this is I short circuit, which is 93.8 milliamp. So then there's a drop. Okay, there's a drop. So the question is, how big is that drop? We can see here by that number that our drop from here to here is how big? It's 406.2 milliamp drop. That's what my guy's showing me now here. Okay, so now what we got to do here is that we got to solve the circuit problem. So I'm going to come back up here. I'm going to grab this circuit here. And I'm going to bring it back down for just a brief moment. And so now here's step 4. We now have to solve the circuit problem. For the voltage of the inductor. Excuse me. Solve the circuit problem for the voltage of the 600 ohm resistor, which I called V of X. So let's go do that. So if I look at this thing here, what I'm really interested in, actually, I think I'm going to change what I'm going to do here. What I really need is that I need the circuit. I don't need the whole problem. Let me grab the circuit and bring it in, just to save space. So here's my circuit. And what I'm seeing with my circuit here is that I don't have the right part of the circuit, of course, right? I don't have the right part of the circuit. I have this part of the circuit. And so what I want to do here is that I want to go in and I want to say, how do I connect, right? How do I connect one of these circuits to the other? How do I connect the inductor current to the, how do I say this? How do I connect the inductor current to that 600 ohm resistor? And the first thing that you're seeing here is that what I have to do here is that I essentially have to look at what? I have to look at how these two are connected. And you could see here is that if I use simple circuit thinking here, is that the voltage Vx is in parallel with the 400 and the inductor. So if I look at this thing, what this is really telling me here is that my circuit looks like this. I have the 600. Let me write it over here. And this guy is going to give me the voltage of the 600 as a function of time. And this guy is in parallel with these guys right here. So this guy is the 400. And of course, we now know that this guy is going like this here. So I know that those voltages are the same. So if those voltages are the same, then what I can do here is that I could come in and I can just use, you could think about it as KVL, if you want to think about it this way. But the bottom line is this. This guy has a polarity of plus and minus. The voltage across the 600 ohm resistor must be the voltage across the 400 plus the voltage of the inductor. However, you could see that the 400 is in series with the inductor, so therefore this must be 400 IL. But the voltage of the inductor, we already know, is given by what? The inductor equation, which is IL dt. So that means I got to use IL, which we saw already was 93.8 plus 406.2 e to the minus 6400 t. So I got to put that into that equation. So here I go. So if I do that, then I'm going to come in and I'm going to say, okay, the first term is going to be what? It's going to be 400 times the inductor current, which will be 93.8 plus 406.2 e to the minus 6400 t. The inductor current is 1/10, so I'm going to write 1/10. And then I got to take the derivative of this guy. clearly the first term is 0. It's the second term that I'm going to do. So you're going to see that I got to bring down a minus 6,400 down. So then when I look at this thing, this is going to be 406.2 times minus 6,400 times e to the minus 6,400 t. And that's my voltage of the 600. So what I'm going to do here is I'm going to clean this up. So you can see here is that I have what? I have a constant term here, and that's it. And then I have an exponential term here, and I have an exponential term there. So I have two exponential terms plus one constant term. Now the thing you got to remember here is that this guy, it has to, all of this has to be multiplied by milli. Okay, everything has to be multiplied by milli. So there's a little m here. Maybe I should do it this way instead. You know what, I'm going to expand this just to make sure that we get this in right. So what I'm really seeing here is that this is times 10 to the negative 3, and this is times 10 to the negative 3. And the units, right, I now have what? Resistance, ohms, times amps, which is volts. So now when I multiply this out, this is 400 times 93.8 times 10 to the negative 3. So if I do that, the number that I'm going to get then is 37.5 volts. Now I have two exponential terms. So you're going to see 400 times 406.2 times 10 to the negative 3. So maybe I should write this out. So this should be 400, 406.2 times 10 to the negative 3. That's the first term, right? That's this whole first term right here. Now I got to deal with this whole term right here. And then I get a second term, and it's going to be a minus term. So I'm going to put minus in here. And you can see the minus is from the 6,400. So then I'm going to get 10, 406.2, 6,400 times 10 to the negative 3. And then this whole quantity is multiplied by 6,400t like this. And my units are going to be volts. So if I clean this all up and I do the mathematics, which you should never trust, if I have a calculator in my hand, and then I'm going to get that this is 97.5 e to the minus 6,400 t volts. And that's the voltage of the 600 ohm resistor as a function of time. So that's our solution. Let's go interpret this thing. So what I really need to do here, if I want to see if this makes sense, okay? Okay, so let's try to interpret. I want to interpret this 600 volt, 600 ohm, 600 ohm voltage here. So now what we want to do here is that we got to ask, we really got to find three things. So the way we do this is that I need the voltage of the 600. I need it for t equals to 0 minus. I need it for t equal to 0 plus. And then what I'm going to need here is that I'm going to need it for V600 as a function of time. And eventually what we'll see here is that we need V600 at t equal to infinity. Okay, so what we got to do here is that we got to go back and we got to look at these things. So the first thing is what happened the moment the switch, before the switch is thrown. So if I come all the way back up here, we saw in the first circuit that the inductor shorted out the 600 ohm resistor. So it starts off at 0. So right away, we know for a fact that this guy here is of the 600 ohm resistor At 0 minus, it's at 0 volts. So now we need the 0 plus. So here's my solution here. So I know that V600 at 0 plus is this solution. So it should be 37.5 minus 97.5 e to the 0. And when you calculate this thing, you could see here that I'm going to get minus 60 volts. Okay. And so I now got that. So I got this guy, I got that guy. I know what is the time dependent, which is our solution. So we got this guy. So what's V600? Well, you could see that the steady state has to be what? This guy has to be 37.5 volts. So let's go look at this plot here. So if I plot this thing, what am I seeing here? So I'm going to plot V600 ohm of T for all times. And this is expected on quizzes and exams. So here I go. So the first thing that I'm going to do here is that I'm going to look at something like this here. So what am I seeing here? Well, it looks like the jump is actually bigger down below. So what I'm seeing here is that my current comes in, not my current, but my voltage of the 600 ohm at this guy is 0 volts. And then the switch is thrown. So what happens now? There's a big discontinuity. There's a huge jump. So it goes from here all the way down. And let's say that at this point here, what we're seeing here is that V600 at 0 plus is now minus 60 volts. So here I am. I'm at 60 volts right here. And then I know that at T infinity, it jumps up to 37.5. So that means here is that this guy's going to jump all the way up to here, which is then going to be V600 of infinity is then going to be 37.5 volts. So what am I going to see? I'm now going to see where this goes up to a higher voltage, like this. So what am I seeing here? Well, my solution is telling me what? Well, I start off at 60 volts, right? Negative 60 volts. And my solution tells me that there's what? There's a jump. Look at the jump. This is telling me that there's a jump. And you know, I should have done this before here. Look at the minus sign here. That minus sign indicates that it has to go to a higher voltage. And that's exactly what we're seeing. And we're seeing that the jump here is how big? Well, it has to be 97.5. So then if I come in here, you could see that the jump from here to here is what? 97.5 volts. Exactly what we would have expected from the solution. So it's looking good here. And then the last thing that we want to do here is that I want to go in and I want to look at what happens to the voltage of the inductor. We already know that so now let's pay attention to the voltage of inductor. And one of the things that I said here is that we expect that VL of 0 minus to not be equal to VL of 0 plus. Are there situations where they're the same? Of course they are. It's the geometry of the circuit that tells us what's going to happen. So now let's go look at this thing. Well, clearly before the switch is thrown, this guy is of course 0 volts without any doubt because it's a short. So now what about VL at 0 plus? Well, the only thing that we can write here is, of course, this guy right here. And if I compute this thing, this is going to be what? 1/10. And of course, we've already taken the derivative of the inductor, right? We took the derivative of the inductor right here. So what I'm going to do here is that I'm just going to steal this piece right here for the inductor. And if I do that, I'm going to get what? I have 1/10, and then I have 406.2 minus 6,400. And then, of course, I'm going to get times 10 to the negative 3, and then I get e to the 0. And when I compute this number, the voltage of the inductor is minus 260 volts. Okay, 260 volts. And so what you're seeing here is that this clearly shows here that VL of 0 minus, which is 0 volts, does not equal VL at 0 plus, which is minus 260 volts. And this is what I mean. Unless the geometry of the circuit forces it to be the same, what we're seeing here is that the inductor does not have the same voltage before and after the switch. So just think about the physics of this thing. For a brief moment, right? What you want to see here is that the 100 volt source in the circuit is dominated by the inductor voltage of minus 260 volts. It dominates this thing. So what you're seeing here is that look at the voltage of the 600 ohm resistor. What it does here, it essentially forces that drop to change across that 600 ohm resistor. However, this is very brief because the inductor is passive. It cannot sustain this guy for very long. And so what happens? Well, it runs out of juice, and essentially the 100 volt source then takes over and charges the 600 ohm to a different polarity, right? The fact that you get this negative 60 volts for the 600 ohm resistor is due to the inductor's negative 200. Let me make sure that I'm saying this right. So the fact that the voltage of the 600 ohm resistor at 0 plus is equal to minus 60 volts, this is due to the inductor voltage at 0 plus being minus 260 volts. But as this thing gets dominated by the 100 volt source, then the 600 ohm resistor then changes polarity. And then what you're finding here is that after a short period of time, the 100 volt source dominates and changes polarity of the voltage of the 600 ohm resistor. And if you look at this guy at t equal to infinity, you can see that this guy then goes to what? Positive 37.5 volts. And that's an indicator that that's the 100 volt source that's actually doing it. Okay, that's the third constant source that I've dealt with. So now what we're going to do here is that we're going to try to make things a little bit trickier, but not too much. And we're going to go to what are called sequential switches. So we really have two more things to cover before we get to the time-dependent sources. So what we really are going to do here is that we're going to look at sequential switches in first-order circuits. So what do I mean by sequential switches? Sequential switches means that I have more than one switch in a circuit and that they turn off and on. I mean, they switch either, open or close at different time intervals. So sequential switches are circuits with multiple switches that are thrown, right, open/closed at different times. Okay, at different times. And what you're going to find here is that every time a switch is thrown, there's a new circuit that's created. So that every time a switch is thrown, a new circuit is created. And so what do I mean by it's created? Well, what you're going to find here is that if a new circuit is created, what I really mean here is that I'm going to have what? New Thevenin Norton parameters. And remember what that means. If I'm talking about a capacitor, then I'm going to have multiple VOCs. I'm going to have multiple, R Thevenin resistance. And I'm going to have multiple time constants. If I have a Norton circuit, I'm going to have multiple I short circuits as well as multiple Norton resistances and time constants. And so again, as an example here, is that we should look at something like this here. So imagine that we have, so suppose we have an RC circuit with the following behavior. Okay, so what I'm going to do here is that I'm just going to sort of like set this guy up to look like this. And of course, I'm plotting VC of t. So let's say that I have the first circuit. Well, if I have a first circuit, what that really means here is that I'm coming in at what? Some initial value for the system. And then right at t equal to 0, just to make it nice and simple here, this is the first switch. So what happens in the first switch? Well, what I'm going to say here is that that means that I'm now going to have a charging or discharging capacitor. So for the hell of it, what we'll do here is that we're going to say that this thing is going to charge up. So that means this is my first circuit, RC circuit. And let's say that it goes up to some value like this. Okay, so that means here is that this guy is going to be what? This is going to be my capacitor for the first switch that was thrown. And I'm going to go from 0 to T, and then I'm going to say all the way to T1. And here's where T1 is at. And at T1, what you're going to see here is that now I'm going to have a second switch that gets turned on. So I have a second switch now. And the second switch, what you're going to see here, let's suppose here that it discharges. So let's call this guy that we're going to follow this all the way to T3 or T2, excuse me. So now what I'm seeing here is that I'm seeing, let's say, some very long time constant where this thing is here. So what you're finding here is that I now have a new equation between T1 and T2. I have a new capacitor. And then what we'll say here is that at this point, at T2, let's say that there's a third switch that is thrown. And this third switch has a very large time constant. And so what ends up happening here is that this thing decays very, very, very quickly like this. And so when I look at this, I'm going to have a third interval that essentially, in this case here, I'll call it infinity. And so what you're seeing here is that at each of these moments, each of these intervals, you have new initial conditions. So check it out. So if I look at this point here, this is my first initial condition for this circuit. And then when I come to here, here's my second initial condition. And if I look at my second initial condition, it's got to be what? It's got to be C1 at T1 will then be my second initial condition. And then you'll see here that I go through the second interval here. There's another initial condition. This is the initial condition for the third interval. And then this guy here is going to be what? It's got to be VC of 2 at what time? T2. This will be my third initial condition. So what you're seeing here is that the problem solving doesn't change. It's just that now you got to be really careful. And what you got to do in this situation here is that you got to really keep track of things. Okay? You got to keep track of things. So what do I mean by that? So now if I start to sort of like conceptualize what's going to happen here, it goes like this. So let's look at the first switch. I don't want to get too high up because I want to keep that. So the thing here is that I have the first switch. So the first switch implies that I have my first initial condition value right there. Now I'm going to use this for my first interval. And when I look at my first interval, what that means here is that now I have a charging capacitor here. And because it's green, I'm going to write this in green just to make it as clear as possible. So now I have a transient behavior. And a transient behavior means that I have what? VC1 of 0 T1. And what should I expect here? Well, I'm going to have a VOC for this interval. Then I'm going to have my initial condition. And then I'm going to have my VOC for this interval, and then e to the minus t. But now I have a time constant, tau 1. Now the switch gets thrown. Okay. So what I need from this interval is that I still have a transient behavior. But this time, check this out. I need VC of 2. And this guy is not at the origin. The solutions that we had before start at the origin. So because this does not start at the origin, start at the origin, we need a coordinate shift. From what? So we're going to go from t to t minus t1. We have to shift our origin to t1 in order for the solution to work. So what you're going to see here is that, check this out. So then I need my new VOC. So here I go. I have a new VOC2. Then I need my initial condition. But wait a minute. What's my initial condition? It's from the green interval. In other words, it's got to be VC1 at T1 is going to be my initial condition. And then I'm going to get VOC2. And then I have a new time constant, but I have to perform a coordinate shift. Right? And you could see there's my shift right here. There's my shift in coordinate system. And then I go to the purple one. And if I go to that one, again, I have transient behavior. But now I have a different transient behavior. And it goes like what? I have a new solution. And this guy's going to be what? At T2 to T to infinity in this case. And this guy's going to have its new VOC3. But then I need the new condition, initial condition. But that initial condition is what the final value is of the previous interval. So then I got to go back to the blue here. And this guy's got to be VC of 2 at what? At T2. And then I come back and I have VOC3, and then I have E, but now there's a different shift. It's not at T1, it's shifted all the way to T2. So then I got to go T minus T2, and then I have a new time constant. So these are the ways that you have to approach these problems here. So what I want to do here is that to emphasize this kind of thinking, let's go do it. Okay, let's go do this thing here. So the example that I want to look at is this guy. So remember, the hardest part of this is just keeping track. So you're seeing here is that there's two switches. And because there's two switches, we have to just keep track of the things that we've got to do here. Okay. So let's go do this here. So what I'm expecting here is a very similar thing before. So here, we're only really looking at the red, the green, and the blue. There is no third switch. There's only two switches. So this is, I mean, this was fairly complicated, but I just wanted to stress the points of what actually happens here. So let's go do that. So the first thing that I'm going to do here is that I'm going to get the initial condition. Okay. So when I look at this thing, I see that there are 3 time intervals for 2 switches. So here we go. So the first circuit, which I'm going to call circuit number 0, what I got to do here, since I have an inductor in my circuit, the thing that I'm going to pay attention to here is that what is that inductor doing? So when I look at that inductor, what I'm going to do in this circuit here is I'm going to do what? I'm going to determine IL of 0 minus. So that means When I look at the first switch, it's open. When I look at the second switch, it's closed. This guy will not open till 51 milliseconds. So here I go. So at t equal to 0, what is my circuit? So I have a 52 volt source. I have a 6 ohm. Then look at my switch. My switch is open, so I'm not even going to put that there. And then I have my 12. And then look at that. I have a 6. And then finally, I have a 2. And then my inductor at 0 minus should be what? A short. So what I know here is that this guy must be L of 0 minus for that first circuit here. Now, what we're going to do here is that this time I'm going to, because I want to calculate the voltage of that 12, let's come in here and say, this is the current that I'm looking for right there. So if this is the current that I'm looking for here, actually, I'm going to put this down here so that I could write it. I'm really looking for I12 of 0 minus. So what is, I'm going to need those two values here. So let's go look at that. So the first thing that I'm going to do here is that I could see here that the current through the 2 ohm resistor is really the volt. The way I'm going to get it here is I'm going to use VDR and Ohm's law to do all of this work here. So I'm going to use VDR and Ohm's law to get IL0 of 0 minus. So here we go. So I'm going to calculate the voltage across the 2 ohm resistor. So if I calculate the voltage across the 2 ohm resistor, VDR tells me what? It tells me that the voltage across the 2 ohm resistor, now look at this thing. I have a 2 and a 6 in parallel are in series with the 6 and a 12. So here I go. So if I want the voltage across this, I have a 2 parallel to 6 plus 6 plus 12, and this should be 2 parallel to 6 times 52 volts. So if I compute that, I'm going to get 4 volts. So I now know what the voltage is across that 2 ohm resistor. But note, this is, so then if I look at Ohm's law, then I know that the current of that 2 ohm at 0 minus is then going to be, according to Ohm's law, it's going to be the voltage across the 2 ohm divided by 2. So if I do that, I'm going to get 4 divided by 2. It's going to give me, of course, 2 amps. And so now I have IL of 0 minus. So I now know what the current of the inductor is. Now, while we're here, I'm going to get the current across the 12 ohm resistor. So then I'm going to solve now for I of the 12 ohm resistor, that guy right there. And you could see that I'm going to, because of this, there's a couple of ways that we can do this. Let's look at KVL. If you look at KVL, look at that the voltage across the 2 and the 6 is 4. Well, maybe I should just use VDR. It might be faster to use VDR. So I'm going to use VDR and Ohm's law again. Okay, so if I look at VDR, because it's the same type of calculation, I see that the voltage across the 12 is going to be what? 6 plus 12 plus 2 parallel to 6 divided into 12 times 52. And if you compute this, you get 32 volts. Then from Ohm's law, I could then now get the current of the 12. So I get the current of the 12 at 0 minus is then going to be the voltage across the 12 ohm divided by 12. So in this case, you're going to have 32 divided by 12. You're going to get 2.67 amps. And now I have that current. So I'm going to do this in a different color. So this is what I'm going to look for when I go to solve the circuit problem. So now I got this. So now what happens? The switch is thrown. So if the switch is thrown, I have a new circuit. So look what happens. If the switch is thrown like this, what happens? It kills off the 52 volt and 6 ohm resistor. It shorts out the source and the resistor. So I have the following circuit here. So here I go. Circuit number 2 or circuit number 1. And what I see here is that I now have switch is thrown. Close, which implies that you short out 52 volt source and one of the 6 ohm resistors. So what actually happens? Well, my circuit looks like this. So I have a resistor like this. That's the 12 ohm. Then I have my 6. And then I have my 2. And then I have my inductor. Okay, that's my circuit right there. And what we're looking for is we're looking for what? We want the current of the inductor for this new circuit as a function of time. And the other thing that we're going to be looking for is that we're going to be looking for this guy in this new circuit right here at that time. So the current has to decay. It's a passive element. So now what I need here is that I'm going to keep doing the same thing that we did. So to solve the circuit, I'm going to start to go through the steps here. So the first step here is that I need to determine IL of 1 at 0 minus. Well, the inductor has to have the same value here. So then that means here, when I look at this guy, the initial condition here is determined. We already know what it is. The inductor current cannot change. So if the inductor current cannot change, this guy at 0 plus must also be 2 amps no matter what. So I now know what the initial condition is. So then the next step here is I need my Norton parameters. So let's go do that. Note that there's no source in the circuit. No source in the circuit means I short circuit must be 0. So this tells me here is that when I look at that, if I look at my I have this immediately tells me that I short circuit for this circuit is 0. There's no source in the circuit. So then I need my Norton resistance. So when I look at my Norton resistance, I'm going to remove the inductor. And so I have this circuit right here. And so here's a 12, here's a 2, here's a 6, and I need my Norton resistance right in here. So you can see that I'm going to have 2 parallel to 12 and 6. And so if I write this out, then I'm going to get what? I'm going to get 2 plus 12 parallel to 6. And we know that 2 parallel to 6 should give you 4. 4 plus 2 gives you 6 ohms. So now I know my Norton current. So the thing that's going to be different here is that, oh no, the other thing that I got to do is I got to go calculate 1 over tau. So here I go. So 1 over tau 1 is then going to be what? R Thevenin 1 divided by L. So in this case, we just calculated 6 ohm. I don't know what L is. L is 1. So then this is going to be divided by 1 Henry. And so therefore this has to be 6 Hertz. And that's 1 over tau 1. So now I have all my Norton parameters. So I'm going to write my solution here. So my first solution looks like this. So for circuit number 1, I have the following thing. I have IL1 of T, and maybe I should be more careful. This should be IL of 1 between 0 and T and 51 milliseconds. This guy is going to be I short circuit 1 plus IL0 of 0 minus I short circuit 1 e to the minus T over tau 1. Immediately we can see here is that this is 0, of course. And then I'm going to start putting in my values, and you're going to see here that this guy should be, what did I calculate for I short circuit? I have 2. My initial condition is 2, so this should be 2e to the minus 6t. And that's going to be in amps. So this is IL1 between 0t and 51 milliseconds. So I now have my current of the inductor for this time interval. So that solution's only valid for that time. So now I need to go determine the current of that 12 ohm. So what I'm going to use here is that I'm going to use this current to calculate what I12 is. And the way I see this here is that that current, I12, so let's write this down. So now we need to determine I12 between 0t and 51 milliseconds. And when I look at this thing, what I'm really seeing here is that note that this current is actually being divided by the 2 and the 6. So then this is really just the current divider rule. So I can use current divider rule in the situation because I already know what the inductor current, whatever's not going through the inductor must then be going through the 6 ohm. So what I'm seeing here is that I can apply CDR to get the current of the 12 ohm resistor. And the way I'm seeing this here is that I'm seeing this way here. Let me make sure that I'm seeing this right. According to the CDR here, I should have that if I want the current across the 2 ohm resistor, it has to be the opposite current divided by the sum of the 2, and that has to equal I12. So if I do this properly here, I should say that the current of the 2 ohm resistor should be the opposite resistance divided by the 2, which is then going to be equal to the incoming current of the 12. But that 2 is going to be what? IL1 of T. So now I can reverse engineer this thing here, and you could see here that if I do that, then I'm going to write what? This is going to be 8 divided by 6, which will give me 3 over 2 times this here. So then if I reverse this, then solving for I12 of T, I'm seeing here that I12 of this guy should then be 8 over 6. So it should give me 3 over 2 times IL. Oops, let me be careful. IL1 of t. And so therefore, I know that I'm going to get 3. And look at my 2 here, times 2. And this is going to give me e to the minus 6t. So therefore, I should have 3 e to the minus 6t. And that should be amps. And that's going to be what the current of the 12 ohm between 0, t, and 51 milliseconds. So I'm going to do that in purple so that I can come back and look at this thing. Okay, so now let's go to the next piece here. So the next piece here that we got to do here is that now the second switch is thrown. So I have a new circuit. So I have circuit number 2, which says that the second switch is thrown. So when I look at this thing here, what am I seeing here?
I think that 3 halves should be a 4/3.
Did I do something wrong? What's 4/3?
When you get 8/6 reduced.
Oh, isn't 8? Oh, gosh, yes, thank you. It's 4/3. You're right. I even said 4/3, and then somehow I didn't do very good at this. So this should be 4/3, and this should be 8/3. Thank you for the help, Josh. Thank you. Okay, so now what I have here is that the switch is thrown. So let's go look at the circuit now. So this is gone over here. So if I throw this switch, look what I'm adding here. I'm taking away the 6 ohm resistor. So in other words, the resistance goes up, because when I have resistors in parallel, I know that the inductor's there, but when we're looking at extreme, like steady state situations, the 6 and the 2 in parallel reduce the resistance. But if I now take out that 6 ohm resistor, I'm going to increase the overall resistance. So I should see a big decline in the current. So let's go draw that. So the 6 ohm is now gone. So if I look at the circuit here, what am I seeing here? What I'm seeing here is that it looks like this. I'm going to have a 12, a 2, and an inductor. So here's my 12 ohm, 2 ohm, and now I'm looking for this guy here, IL of 2, and this guy's going to be for t greater than 51 milliseconds. And once again, I have my current of this I12 that I have to pay attention. And you could see that the current of the 12 must be the same as the current of the inductor. So here I go. I'm going to go through the exact same steps. So the first step that I got to do here, I got to go determine the initial condition. So what's the initial condition? Well, the initial condition is created by what? The interval circuit. And that's that current at what time? At t equals to 51 milliseconds, or I think I'm going to stop writing 51 milliseconds and I'll go 0.051 seconds. That's the initial condition for that interval. That's what it was. So then let's go solve for that. So then I go to interval circuit. So I go to circuit number 1 solution, which we already know what it is. We just wrote it down, and that guy was 2 e to the minus 6. So this should be IL of 1 at t equals to 0.051 seconds is then going to be 2e to the minus 6t. And if I punch in these numbers, let me make sure. Here, you got to be careful. Let's see if I get my calculator right and see if I do it right. Okay, I get 1.473 if I round, and that's going to be amps. So that's my new initial condition. Okay, and this is at t equal to 0.051 seconds. I got that guy. Okay, now that I got that guy, let's go get our Norton parameters. So I'm going to bring this over to here. So then step 2, I need my Norton parameters. And you can see that this will be pretty fast. So you can see that I short circuit for the circuit at 2 is of course 0. There's no sources here. And we can sort of like eye this thing. If I remove the inductor, you can see that the 12 and the 2 are in series. So I'm going to say that our Norton for the second switch should be 12 plus 2, so it should be 14 ohms. So then if I go calculate the time constant, it's going to be what? 1 over tau 2 is then going to be Rn2 times L. So this is going to be 14 over 1, so I'm going to get 14 hertz here for 1 over tau 2. And look at the time constant. We expected this to be a stronger decay because we got rid of that 6, which increased the resistance. So now I want to go put this into solution form. So if I go to step 3, I'm going to put into solution form. So now here we go. So check this out. So I have IL of 2 for the second switch. We agree that this guy has to be greater than that. This is the only time the solution works. I have I short circuit of 2 plus my initial condition at 0.051 seconds minus I short circuit of 2 e to the minus, let's be careful now, there's a shift. How much did I shift it? 51 milliseconds. And then I have my time constant. You know what? I should have put the 14 in first. I'm going to move this over. Okay. And I'm going to say that this is 14 times that. That's my solution. So if I look at this thing, of course, we already know that this is 0. So then the end result of this solution then has to be what? Well, I could see that this is 1.473 amps times e to the minus 14 t 0.051 amps. So now I have my solution for t greater than 51 milliseconds. So, but note that these guys are in series. So I'm going to take this back. And this is also the same as this guy for t greater than 51 milliseconds. So that's really what I'm after. So I'm going to do this in purple here. So if I go write my solution, what do I expect my solution to look like then? So in summary, we have that I12 of t for all times here. We saw that at t equal to 0, what was the inductor of L? What was the 12 ohm resistor? It was 2.67 amps. Okay, so I have 2.67 amps for t 0 minus. Then I have my interval of 0t between 51 milliseconds. So I got to go back and get that solution. I'm looking for purple, and this is it right here. So it should be 8/3. So it should be 8/3 e to the minus 6t.
Carlos, can
And
you
then I
just
have
scroll
my
up a
final
touch?
solution, which is 1.47 e to the minus 14 t minus 0.051. And this is going to be for t greater than 51 milliseconds. So then I'm going to go plot this thing.
Carlos, can you scroll back up a touch?
Say that again.
Can you scroll back up a touch? Perfect. Thanks.
Okay. So what I'm going to go do here is that I'm going to go plot this now. And let's see what happens here. So what I'm seeing here is that it has to look something like this. So if I plot this thing, actually I'm going to plot it over here. Let's see if I can do an okay job on this guy. So the first thing that I'm seeing here is that I have my first plot. So I'm coming in, I have I12 of 0 minus is then going to be 2.67 amps. And then what is going to happen? This thing is going to decay. Now, as it decays, whoa, is that really right? Let me make sure here. So as this guy decays, there's a tiny difference between, right? 8/3 is 8/3 not 2.67? I would think that the answer is yes.
Yeah, it is.
So that means this is not discontinuous right here. This is continuous. So the circuit is forcing that resistor to be continuous. So the thing about this is that I did not calculate this value. I should have. But what you're going to see here is that this thing is going to decay to this point here. And this is going to be at 0.051 seconds. So this guy is going to decay at this next interval. And what I should have calculated, let's just calculate this thing. It won't take too long here. So 2.67 times to this guy's going to be so this guy's going to decay all the way down to 1.97. So this guy's going to come all the way down to here. And let's say that this is 1.97. So this value right here, I calculate this because this is going to be 8/3 times e to the minus 6 times 0.051. And I get a value of 1.97 volts, just sticking to 3 sig figs. So then what happens here? You know what? I'm going to do this a little bit higher. So then what happens here is that I'm going to go here. And so then my arrow then goes like right here. And that's what that value is. So the question is, what happens here? Well, at t equal to 51 seconds, I look at the solution here, and the solution tells us that this should drop immediately to 1.47. So in other words, this thing is now going to have a discontinuity where it's going to jump down. And it's going to jump down to what value? This guy right here. That value should be 1.47 volts. And because it has a bigger time constant of -14, you should see a steeper decay down to 0.
Carlos, you mean amps, correct?
Say that again?
You mean amperes, not voltage.
Yes, I mean amps. Thank you. I definitely mean amps. Okay, that ends this last section here. So, on Tuesday, we start time-dependent sources. Okay, you're going to see that there's a dramatic shift in our problem solving. Dramatic shift. And it's going to go like this. Now, I have a recommendation. You're going to find the problem sets are going to take longer. I would start sooner than later. And believe, trust me, that's a good recommendation after 24 years of doing this stuff. Okay, I will talk to you guys later, huh? Enjoy the rest of your
What
day,
you say.
and I look forward to seeing you guys on Friday or Monday. Yes.
Do you think we should start maybe Tuesday instead of Wednesday?